Welcome, everyone, to another Wolfram Institute live science stream. We are continuing our conversation with Carlos about emulations between formal systems, categorical formulations of these emulations, combined with experimental treatments of the complexity trade-offs involved when you pass from one formal system to another. This is of interest in our study of foundations of mathematics. We used to call it sub-foundational, we used to call it sub-axiomatic foundations of mathematics because we're emulating axiom systems such as Boolean algebra with lower level computations. However, began to suspect that it's not really a matter of going below axioms in mathematics. It's more that we're developing a theory of general emulatory passing between formal systems, and it's quite exciting. It's coming along well. It requires some generalization, which has in turn motivated a more serious push into mathematically formalizing our treatment of hypergraphs, as well as beginning to actually develop complexity measures for hypergraph rewriting rules, which is quite exciting. We haven't spoken about this in a little while, Carlos. So let's review what's new.
Yep.
What's happening now?
Give me a second so perhaps maybe we can, okay, because I plan to divide this in two halves roughly in terms of discussion. So first half, or one of the halves, depending on how my tablet responds. Because we didn't change the meeting, that's why I cannot join. Okay. So, because
this is a good thing to set up. This is a good thing to set up in advance. In hindsight, yeah.
Yeah. I mean, at the moment I didn't think, but yeah, we are at the internal meeting link, right? So.
Yeah.
So anyway, so for one half, for the viewers' benefit, for one half, I want to give you a perspective of what I'm currently working on mathematically to figure out these complexity measures, which is kind of a preliminary step where you have to figure out, or at least decide, which form of spectral theory you're going to take. We need to generalize spectral theory for hypergraphs. We need to have this to do something like von Neumann entropy, and so we need to know what kind of problem we're tackling. So this is the first thing that we need to sort of make clear and for everyone to understand what we're trying to do. And the other thing, oops. Okay. No. That should be fine now. Is that okay?
Yeah.
Are you getting feedback again?
No, it's okay now.
Okay. Yeah. So, right. And the other thing is, at the same time as we do this more theoretical work, purely mathematical work, we're starting to develop the computational functionality to deal with hypergraphs themselves. And Nick will showcase some of the stuff that we were working on together in the last few days. And we can discuss particular desirable things to do with it, although we're going to be still doing it because it has to be done and it's not trivial, and we have to work there. So that's ongoing process. So we can do this in either order. I mean, for the spectral theory kind of overview thing, I just prepared some lecture on my whiteboard. For the other thing, Nick can show some functionality. I can discuss what we are trying to do and what is being done. So whichever order you think it has more priority in case we want to squish the second part to be shorter or something.
Why don't we begin with the computations?
Sure.
And then I'm not sure how long it'll take, Nick, and then we can dedicate the remainder of the Zoom, which I imagine will actually probably be the majority, to the theoretical discussion.
Yep.
So let's see what you have.
So before next, maybe Nick can start sharing, but let me preface what we have actually decided to do this documentation development kind of pipeline that Nick suggested, where we set up this GitHub so that I can start to write the desiderata for functionality, and then he can start to develop some functionality, and then I can develop some prototype functionality on the side and kind of do a workflow that is much more than, let's meet. I see something from Nick's wisdom and then he disappears and then I'm kind of lost for a while. So it's much more efficient in that way. And so
Good.
one thing. So
Yep.
maybe I can before you share, Nick. Let me show the notebook that I have for the functionality summary that we're sort of aiming at, for the one to take a glance at. Again, this is way too many windows for my liking. Hypergraph functionality. Yeah, I mean, maybe again. Okay, I'll just mention it in saying. So we're going to. I mean, perhaps for the benefit of viewers, let's just put it on the screen. So let's share on Zoom. Oops, can I share? Oh, it was just super slow. Okay. Hypergraph functionality, share. Right.
Yes.
So the first important thing is we're going to be focusing on unordered connected simple hypergraphs, mostly because there's this fundamental fact that you can always express any other kind of hypergraph as some symmetric structure on top of an unordered simple hypergraph. In particular, you can have redundant duplicates, sort of degenerate edges by the labeling of an undirected simple hypergraph. So within that category of hypergraphs, we're going to develop visualization, so something that actually renders hypergraphs of arbitrary order in 2 or 3D. We're going to have generation, meaning some kind of generative iterated algorithm that just outputs hypergraphs with given constraints, perhaps. We're going to have a way to computationally encode hypergraph maps and isomorphisms. This is likely to be quite basic, meaning isomorphism is likely to be just direct pattern matching in Wolfram language or whatever we're dealing with. And of course, then metrics that can be taken from them, hypergraph embeddings, motif detections, and then so perhaps one of the things that I have this note here just to clarify that discussing with Nick and Richard, we arrived at the conclusion that we are going to have, I mean, Nick is going to show probably some of this stuff in much more detail, but conceptually what hypergraphs are going to be, formally for us, are going to be lists of vertices, which are just blank labels in some sense, and they're going to carry a type. And this type is kind of a symmetry type. So they're going to carry something like unordered or sequential or, you know, in many to many or whatever, right? And so I think Nick can show this in much more detail, but conceptually that's kind of how the data structure of a hypergraph is going to work. So it's kind of refining a little bit what the Wolfram Physics project does already. And so one of the main immediate goals that we have, once we have the basic functions that Nick is going to show, is to start doing some basic taxonomy and even some actual classification. By the way, for viewers watching, because I see a few you pruts in chat, hello, means of distraction, everyone's here. So the difference between taxonomy and classification is that taxonomy is just a way of sort of organizing stuff and sort of putting things in different boxes that makes things tidy. And classification is a mathematical procedure. So classification actually exhausts types of hypergraphs by some parameters, right? So sometimes if you're doing it discretely and kind of computationally, sometimes classification is called also enumeration in some sense, right? You're exhausting your possibilities. And then something that I would talk more about in the second half of the meeting is associated arrays or hypermatrices that has all this algebraic spectral theory and so on. So maybe Nick can go on and show some of the stuff that we've done.
Well, it's not like they have an actual new functionality. It's whatever I already showed, this idea of having computable...
Wait, I have a question. Carlos, wasn't there more in the notebook that we were just looking at?
Not really. I mean, I use that as like some... I mean, that was just the summary notebook for the functionality. Like the functions are actually across the backlet that Nick's doing and some of the notebooks that we're using to make the functions.
Okay, fine.
Right now we just have a backlet. We just set it up so that there is some documentation. It's almost empty right now. There's like free representation of a hypergraph with arrays, and some new plotting functionality that we've been developing, and that's it. So
Wait,
the
can I just ask a
hypergraph object,
high level question? So Carlos, that list that you provided,
Yeah.
is that a to-do list where some of those functionality requirements have been completed, or is that a list of things that have been done already?
So that's a list of things that we. So I don't know if you want me to show it again, but that's a list of things that we are going to have implemented in functionality. So some of it, so a lot of it can be done already in Wolfram language. Like it's not that we have to do that from scratch, but we are deciding. So for example, the basic data structure is decided. Nick maybe can show that, and we are doing kind of we're investigating what can be extracted from a lot of the physics project stuff, other parts of the repository, and see how we are gonna have that package of functionality eventually. So
okay, so in the future, in subsequent meetings, partitioning this between two different notebooks is somewhat confusing. It'd be nice to have that list, and then for some of those criteria that have been satisfied, then providing examples from the Packlet.
sure. Yeah.
Because I imagine that this is a Packlet definition notebook. It's not going to be organized in such a way where it's obvious which of these functions is fulfilling which of those criteria that you were listing in the other notebook. Now Nick could describe it, you could describe it, but I think in the future, I'm glad that you listed those. It would be good to have updates where you're showing the things you want to do, and then when you've achieved it or you've made some progress, you lift the functionality from here and actually show the example.
Makes sense.
Okay.
The thing is, I completely agree. It's just that today we actually set up this sort of documentation-based development where we're gonna coordinate that way. So it was kind of still in between places. I mean, for next time it should be much more streamlined and much more centralized. I can always extract and make it in the format that you say, which is much better. Yeah.
Okay, so which of those criteria do you want to discuss first from that list, Carlos? Like what?
So Nick did a very. So I think basically in order. I think so. Nick maybe can show how we are encoding the hypergraphs and with the type symmetry and so on. I mean, it's just a matter of looking, glancing at it, and then we can look at some visualization that also work quite nicely.
Okay.
Yeah. So here's examples. Yeah.
So the idea would be to get some hypergraph object. You can format it nicely. It's not like just this plus of hyperedges that we have now, that I have right now. So that it, at least now, it just differs from just this list of lists that we usually associate with the hypergraph. Right? It's some kind of object, and
by the way, Nick, very quick comment on that, just for the audience as well. That notation is actually very good because this O plus notation is actually the basic operation of additive union of hypergraphs. So it's also technically true that hypergraph is the additive union of those three hypergraphs separately, right? So it's a very good, other than separating it from traditional list notation.
Yeah, just
it's very good.
So we like the circle. We like the circle plus. Why the decision to remove the commas, by the way? Does that also have a significance?
I don't know.
No,
it felt like it looks nicer.
It is just better. I mean, overall, notationally.
But in this case, it's an aesthetic choice.
Not really.
The circle plus is actually. You don't think it's okay? What's the motive then behind?
So the circle plus. I should have said this maybe in the summary because it was one of the answers I didn't comment. The circle plus is the operation of additive union as multisets, right? So it's not just a cosmetic change commas for O pluses, but it's the fact that you can have a collection of these things separately, and you commutatively and associatively you O plus.
I'm referring to not to that. Hold on, let me bring out my little marker.
So there's no commas over
here. Yes.
Okay. Sorry. Yes.
You could argue that comes from lack of ordering, maybe.
Yeah, commas are redundant in that context completely.
Yeah, it just adds more noise.
Yeah.
You can.
I think it looks better. I just wanted to know if there was a mathematical rationale. Like the circle plus operator has a mathematical rationale. Is this an aesthetic rationale or?
No, I just actually seen this notation somewhere.
Yes.
Okay.
So the notation
Okay.
comes from my theoretical summary, the document that I was working on, because the notation was you do set enumeration with comma separation. So you mean that each symbol signifies a different set element, and then you do tuple element separation with no commas and curved brackets, and then you do bag separation with no commas to signify. Sorry, you do bag elements with curly brackets and no commas. So you have
no commas.
Yeah, basically.
Okay, good. This is okay. Yeah, this is meticulous. Excellent. Okay.
So right now, a hypergraph is supposed to be this edge list, right? And some symmetry which we don't yet like work with at all, right? But in the end, the symmetry is supposed to show all the symmetries of each individual hyperedge. Or if it's uniform, it just shows the symmetry of the whole hypergraph. And it's like right now I can ask for symmetry is going to be always an empty association. But the idea would be to add different kind of symmetry to like this. It's like the first hyperedge would be one list of cycles, meaning that you can swap first two vertices within this hyperedge, right? Or there's no symmetry at all, meaning that it's completely directed, right? Or you just have an arbitrary list of cycles like that, permutations, so that you form a permutation group around vertices within each hyperedge. So that's going to be what symmetry means. Or you can actually contain some named symmetries, or you can make like some shorthand notation like that. Like every hyperedge is cyclic. You can have symmetry.
How will we use this?
Well, it's going to be used for, I don't know, depends on what functions. Like maybe we can use those in visualization, right? When we know that the hyperedge satisfies some symmetry, you can show some arrows or
if you're asking for more generally why this symmetry encoding is necessary, I mean, this is basically the definition of hypergraphs, right? The mathematical definition of hypergraphs requires this symmetry treatment. So because you must either at the language level encode what your symmetries are by saying everything is going to be either directed, undirected, cyclic, whatever, or if you don't, like Wolfram language does, which has this list structure by default, then you have to somehow specify the kind of symmetry that your edges have. Because even for the simplest case, which we're aiming at first, which is the undirected edges case, we need to specify that by saying, well, all permutations are equivalent, right? So we have to have that entry.
Good.
We can come up with a bunch of named ones too.
Yeah. Exactly. You can have some standard name ones direct. Yeah, exactly.
Is there any other names you have in mind?
Cyclic. Not really. I mean, maybe tree, but whatever.
Tree? Like binary?
Yeah.
Or maybe.
But yeah, that doesn't. Yeah. Oh yeah. I mean, okay. There's another one. It's alternating.
Each pair can be swapped, right?
Yeah.
Maybe.
Yeah, but this is just some. At the moment, we're gonna look at undirected.
Right.
Oh wait, there's unordered and undirected.
Oh, it should be like a synonym, right? Ordered and directed is the same thing.
No, it's not the same thing. For undirected and unordered, I think they can be the same thing, I guess, but directed normally means many to many. So directed usually means several inputs to several outputs. It's like a generalization of directed graphs, like direct generalization.
Okay.
Ordered, I would normally call sequential, but this is just naming. I mean, maybe we should.
Okay, you guys can settle this.
Yeah, we didn't need to spend too much time.
But I understand the motivation.
Yeah.
Okay, what else? What else do we have?
No, not much. It's like I also had this algebra, because it's a union. You can actually, if you have a bunch of hypergraphs, you can add them or multiply them.
By the way, what in the multiplication? Which multiplication did you use eventually? Because we talked about this.
I don't know. This is like This is like outer product. You can
Okay, yeah,
so
because
this-
this was a thing that I actually spent a couple of days, maybe a day and a half, maybe not 2 full days, but I had to. This concept of Cartesian product of hypergraphs is not
Yeah.
really settled, and I read 2 papers on this.
Well, this
so
is like what made sense to me, because if you had like, I think I have 2
Yeah.
unities. Like I have maybe this is like an empty hypergraph. If you add it, it's not
Yeah.
gonna change. But if you multiply it, it's gonna like make it a 0. And I also
that's a
it's a-
good property.
and I also have like, if it's a hypergraph with a single 0 arity or 0 order edge, like this, right?
Yeah.
If you multiply it, it's not changing, right? It's the same as this is before. So it acts as like multiplicative unit,
Okay.
yeah. And if you add it, it just adds 1 more. So it's not.
So is it the case that, Nick? Is it the case that the product hypergraph has vertex set equal to the Cartesian product of the vertex sets together,
Yeah, something like that. Yeah.
and then the edges are all the possible pairs of
Yeah,
edges
that's
with
like an outer product basically. Yeah, it just.
Yeah, that's the standard. That's the most standard definition of Cartesian product I could find. Now there's basically this idea that whatever you defined some combinatorial structure, like all the symmetries that we have above, you basically have the equivalent product at the level of full hypergraphs. So that means we don't really have to worry too much in terms of the product immediately, right?
Like since you're trying to define category, that maybe it's better to just first define morphism between hypergraph, and then you will have natural Cartesian product.
Well, I mean,
as a universal object in that category.
Yeah. I mean, that's. I mean, the problem is, I mean, the categorical product will tell you. It will not tell you how to construct it. Right. So.
Yeah, but it will basically settle the discussion, because like there'll be only one definition of product compatible with your morphism, so it's actually well-defined category.
But the problem is that there are many ways of defining categories of hypergraphs. So at each step, we're going to find several possibilities, because we know there are several notions of product anyway.
I'm only mentioning that there's need to be this compatibility between morphism and the product of graphs.
That's a good comment. Yeah, that's a fair comment.
Yeah, I mean, we have a notion of morphism of categories, of morphism of hypergraphs. So, but there's several levels of granularity that you can go with morphisms, and depending on that, you get different notions of category of hypergraphs. And so that freedom mirrors the freedom of products more or less, right? So it's I mean, the freedom is there. But anyway, I mean, maybe we can show also some of the visualization. Nick?
Sure, it's called simple hypergraph plot. Right.
Yeah.
It's almost like it's in a way simpler that we already have like for Wolfram model plot. But it works better for small hypergraphs. It's more colorful and actually can distinguish hyperedges.
Yeah.
The idea is basically the same. Take the graph embedding, but make it more colorful. I don't know.
Can you show some of the 3D ones?
Can we see? Yeah, can we see?
Yeah, and
a
you
plot?
can go 3D. Yeah.
Wow, look how far we've come. Can we see a visualization of that product, or is that going to be too explosive?
I guess we can.
Yeah.
What is the 3?
It's 3D.
Well, does it go up higher than 3?
Well, in theory, yeah, but it's not gonna visualize it. I disabled it. Now
It
it
opens a
only
portal
works
into the higher
with
dimensions.
2 and 3. Maybe I should just have 3D version and that's it. I know,
Yes.
by
Yes,
text.
I think so.
It depends on layout. It shouldn't be that long, but because I've been playing with weights and other stuff. I don't know. why it takes so long. Not sure.
What are these little rings around the vertices?
Unary edges.
Yeah, those are lunar edges.
Order
You have
one.
multiple of them. You just stack those circles around.
Yeah. If it's simple, it shouldn't render more than one, but yeah.
Right. This is very nice.
Yeah,
That's
but this is very nice because the idea, by the way, with this functionality, James, it's not just to see some nice looking simple hypergraph, but this is meant to be the skeleton for all the arbitrary hypergraphs that we can ever render, right? So we plan to spend some time just working with this case with undirected, unlabeled, and be as sort of simple as possible. I mean, pun intended in this context, and then we can go and apply much later, just make sure that we have some general way of labeling and some general way of visually encoding symmetries, and then we can do everything much more efficiently. Because, by the way, for the viewers' benefit, these are the states of the rewrite systems that we are thinking will encode the different formal systems that we are interested in, right? So that's why we're working on this right now, because we want to have sort of like the architecture to build on top the expressions that we want, like statements in some formal language or expressions in some algebra, or diagrams in category theory. Those things could be commutative diagrams in category theory, and you can imagine the triangles as, for example, either operads, or you could imagine them as monoidal categories where you have morphisms from tensor products of several entries into some tensor products of other entries. So things like polycategories or multi-categories, things like that. So these diagrams, these hypergraphs are meant to be extremely flexible, and having a good basic rendering system, I think, is going to be very important, because we never want to. I mean, the thing is, these diagrams will never have to blow up too much in size, because they are meant to be diagrams. They're not meant to be computationally generating something in some limit for very big numbers or something like that, right? So this is where how we will visualize rules, how we will visualize the atomic rewrites of our formal systems, and so on. So yeah, it's a very nice thing to have, and we'll basically have all these functions, all the functionality I described before for these kind of structures.
Great.
Okay, Nick, something else you wanted to show off?
With hypergraph, oh, I don't think so. No.
What was this thing I saw below with tensors? Hypergraph adjacency tensor.
I did show it at some point already.
Oh yeah. Yeah, maybe just remind them.
I think it's broken right now, but I'm not sure.
Oh, really?
Well, maybe let's.
Yeah.
Yeah.
But those three representations, array representation of hypergraphs, the adjacency tensor, hypermatrix, and incidence matrix. Right. Those are three representations, and I have functions that go back and forth to hypergraph, to this array, and back.
Okay, Carlos, could we go back and look at that list that you presented before Nick showed his nice functionality?
Yeah.
Okay, so visualization, that's coming along quite well.
Yeah.
Generation, well, so are there any other obstacles to generation, or do we have arbitrary generation?
So this is also to the point of this O+ notation that we're using. So there's the basic generation operation is additive union, right? In this context, and so one can always generate more hypergraphs by appending more parts, but obviously eventually we want to rewrite these things. But so by generation, we're thinking more in terms of algorithms that directly generate hypergraphs, and there are some standard ones, and I think if I remember correctly, some of the physics project stuff, Nick, does this already, right? Like it has some basic generation for given sizes.
So the whole Wolfram model is about generation.
Well, of course, yeah, of course. But what I mean
Or
is,
you can enumerate like give it a signature, how many hyper edges of this order and so on, and generate a bunch of them.
that's what I meant. Yeah, yeah. So there is, yeah, for generation we have some basic functionality that is gonna do well, I think. So no obstacles.
Do you want to perform rewrites on these hypergraphs?
Yeah, that's eventually.
So you take that kind of hypergraph that you had before visualized, and you'll apply some rewrite rule to it, and you'll be able to get
Yeah.
new hypergraphs that way.
Yeah.
Okay. Now
I guess we also wanna explore how to do rewriting directly on arrays, and maybe on hypermatrices directly.
Yeah, this is the bottom line, that eventually
Oh yeah.
all this functionality, it's great because I mean that is the hypergraph functionality that is kind of more general than just for the project that we have at hand. But eventually, yeah, we can write everything in arrays and maybe work directly on arrays, and maybe that's faster, and we have the functions there.
Okay.
But the idea is the rewriting. So at this point, as we discussed in the last meeting, I think at this point what we're doing is we're setting up the hypergraph stage for the rewrites to happen. So when I say generation,
Yes.
I mean kind of all the ways you can generate hypergraphs that is not directly by encoding hypergraph rewrite rules, meaning things like by size you can append new edges and things like that, which are all particular cases of rewrite rules in some very general sense. But in this context, they are more like the user end control that you get without the need of specifying rewrite rules. So for example, this O plus is the basic one. It's like you have two hypergraphs, you put them together, that's a new hypergraph, right? And yeah, so rewriting is at this point not the immediate goal. Like we are just setting this up for the hypergraphs to work. Then we will have to figure out how to do labels, which should be quite easy, I think. And then the rewriting happens on label hypergraphs, and that's where there's quite a lot of bookkeeping that needs to be figured out, because that's what makes the statement that I made a while ago, that rewriting systems of label hypergraphs are sufficient for this formal system emulation, is specifically because they are labeled, not because they are.
Then why not put labels and also rewriting on this list? You're saying that they won't be immediate, but
yeah, we can.
Those are two objective.
Yeah. We can put them.
Yeah,
we can put it there.
I'd add them. Yeah. Labeling, rewriting.
Yeah.
So I'm just going down this list. So for hypergraph maps,
yeah,
what functionality do you have in mind for these maps in particular?
Yeah, for maps, I think. I mean, normally when I work in Wolfram language, maps are associations, and maybe Nick has a different feeling, but I feel that hypergraph maps should just be associations, so some association-like object between hypergraph structures that we have already defined, right? So because mathematically what a hypergraph map is a set map between vertices, and it's a multiset map between edges. Maybe multiset is redundant here. If we keep track of types, there's no need to keep track of multiset. And we are considering simple, so there's no real redundancy there. So you have these matching types and orders, right? It respects type, it respects type and order, right?
Okay.
So in the Wolfram language implementation that we're doing, I think it's going to be sufficient to just say, well, there's an association of essentially a pair of hypergraphs and an association between their elements, right? So that's why we have this list, and it's not like, oh, we're gonna have like, several 200 lines of code per each of these items, because some of them are going to be, oh yeah, this is just this definition of the, it's very,
sure.
But the others are like huge. Like how do taxonomies like?
I remember we had this discussion during the last meeting where we were distinguishing between, on the one hand, the actual presentation of the rewriting rules between hypergraphs, and this also more general, these maps as you're putting them, that are useful for defining and constructing the hypergraphs in the first place. I think that was the discussion we had last time. These hypergraph maps, these are not. This has nothing to do with rewriting.
No.
This is just this. We just need these for defining properly and constructing these hypergraphs. Just making sure.
Exactly. Yeah. So that's why I kind of give the general one, which is hypergraph maps, and then the specific one is isomorphisms, which are the ones that are most important for us immediately, because these are the ones that are going to, be in the algorithms that generate, be in the algorithms that count stuff, and that, for the metrics and so on. That it's kind of a logical order of the things that are necessary. The dependencies are kind of in order in that list, because when you count stuff, you want to make sure that you're counting different stuff. And so that's why you need some technical implementation of isomorphism.
So based on the overall methodology of the project, the metrics are crucial. The rewriting and the labeling also quite important. I mean, these are all important, but I'm.
So James. So when you said having labeling and rewriting visible for people to see, that's great. But so hypergraph embedding and motif adjacency and this motif detection stuff, that's kind of the prerequisite for rewriting, right? Like that's essentially what rewriting is going to do, right? So that's why it's high on the list, because once you figure out how you map between hypergraphs, which is basically already figured out, this is not a problem. Metrics are just ways of counting stuff, and this is already discussed. We don't have to spend too much time in there. The next thing to do is to figure out how to exactly detect motifs on hypergraphs, which is mathematically embeddings, right? If you have a hypergraph,
my question was this order deliberately constructed? And it sounds as though it was.
Yeah, there is some
prerequisites.
Yeah, there's some sense of dependency, especially in the first few. That's the order of things that we need to do things. And additive union operation is just there. It could be anywhere. It could be after visualization or at the top. Some things are just there. But in order to do motif detection and to do so it's the prerequisite to rewriting rules more generally for labeled hypergraphs. We need maps, we need metrics, we need these basic things. Maybe not metrics, but we want metrics as well for the complexity measures anyway.
Now, regarding the metrics, besides the task of building the functionality for performing the measures, on the theory side, have we decided upon a list of candidate metrics?
Yeah, so hypergraph metrics,
more or less definitively.
Yeah, so these are different. So I'm referring, when I say metrics, I mean things that are just countable from a hypergraph, right? So these are not things like complexity measures or anything like that yet, right? Because that's going to depend on the So for now, metrics are going to be sizes.
Go ahead.
Yeah, metrics are going to be sizes.
We'll use the.
Sorry.
We'll use these metrics. I mean, the idea, again, just for viewers, for everyone, is we will represent a rewrite rule with technically 3 hypergraphs with particular attention largely towards 2, one on the left-hand side, one on the right-hand side. There's also a context hypergraph. Still not clear to me how what role that context hypergraph plays, if any, in this particular case. So we have these 2 hypergraphs. We pick a measure to apply to both, and the difference between those measures is going to tell us something about the degree of computational work that's being performed with each of these rules. But the question is,
not
Carlos,
quite, James. Not quite. So, after the discussions we had, I think we all agreed that it should be a complexity measure that should be taken as a difference between the two, not a metric, right? Because
yes.
Because a metric could be, they can be actually isomorphic, or they can be actually the same size, but happen to reshuffle a lot of stuff. So there's actually a lot of change in some sense.
I agree.
But so they should be comparisons of complexity measures and not just
measures.
Metrics. Yeah.
I agree. That was just a.
Yeah.
I just misspoke.
By the way, there's a question in chat, I guess, for Nick. Pritz is saying, speaking of defining hypergraph products, if the hypergraph A has only length 2 hyperedges and B has only length 3 hyperedges, it looks like the hypergraph A times B would have no hyperedges at all. I don't think that's the case, right? With the product that you had.
No, I don't think so.
Yeah.
It will combine them together.
Yeah.
It's gonna contain 5 length hyperedges.
Yeah.
Well,
Okay.
we've almost run out of time.
I mean, we started late, so we can go. I mean, we've been online only for 40 minutes.
I see. Okay. Just on this before we pivot towards the theoretical discussion.
Yeah.
This ordering makes sense. I like the functionality that we've reviewed today. If we can proceed so that by the time we have our next meeting, we're discussing metrics and motifs, I'll be very happy.
Yeah.
Especially since these other ones you're saying are probably not terribly complicated.
Oh yeah. Should be fine.
Implement.
Yeah. Should be fine. Metrics and motifs next time. Should be perfectly fine.
Good. Okay, great. Well, if we can continue this conversation for another 20 minutes or so, why don't we pivot now towards the theory discussion?
Cool.
And Carlos too,
Yeah.
as we see on our Zoom. Oh, Carlos is the Institute. Okay.
I'm the Institute today because of lots of admin going on. Okay, so before I move on to my Blackboard, let me open up another notebook, which I had ready. So one of the things that was agreed, I think, in not the very last meeting, but the meeting before, was that I would go on and do some review of hypermatrix people and research and things like that. So I'm gonna start sharing very briefly what this is looking like. So hope everyone can see this.
Yep.
Yeah. So a quick summary of this research. So this is the context of which this is going to be relevant is that these hypergraphs have associated adjacency data, right? They are essentially just that in a graphic way, therefore the name graph or the term graph in the name. But we also have these matrix encodings of them, and we have several ways, incidence, we have adjacency and so on. So we eventually will have to deal with this notion of having to operate these matrices together, having to operate these big arrays containing the adjacency data or incidence data of these things together. And so something that we're going to have to contend with in this project, one way or another, is what is this algebra, right? How do we do operations with these things? So the history of this higher order tensor algebra and things like that is actually quite sparse. Some people might find it very surprising because you always think of tensor algebra as, in physics, you have all this tensor stuff and the tensor networks and all this kind of stuff. But funnily enough, most of that is just a way of doing multilinear algebra, which is several copies of linear algebra, which is fundamentally binary in some sense, right? It's based on adjacency, in 1-1 adjacency. So a brief history of this goes back to sort of the cybernetics era and people doing this before people had completely collapsed onto linear algebra for digital systems and things like that. There was actually papers written on this completely general ways of operating logical statements, and so they had like several entries, several outputs, and so on. And you have a very sparse but continuous history that goes until the early 2000s, and then it basically dies. There's a revival in 2008, 2009 from the side of physics, and some connections to possibly quantizing color interactions in nuclear force, strong nuclear force, and so on. And then there's a little bit of a revival, and then some people pick it up, particularly Eddie Nang, and they start to develop a little bit more the rigorous theory of this hypermatrix stuff, this sort of higher order matrix theory. So I can say that I myself, together with Xerxes and Tali, we actually contributed some new results in this direction recently, but it's otherwise a quite sparse subject. So what is the main problem here? The main problem is that we need a notion of spectral theory to do these complexity measures on hypergraphs, right? Now the problem is, as I say here, is that hypermatrices do not suggest a single notion of an eigenvalue problem. Right? We don't have a single notion of an eigenvalue problem anymore. And I will go into details on the Blackboard in a second. So there's one of the reasons is there are multiple choices of closed operations between hypermatrices, and there's also the nice fact that hypergraphs actually suggest a canonical way of doing these operations. It doesn't select one of them, but they suggest a way of systematically constructing these operations. So it's kind of a match made in heaven that we need to have a way of doing operations on hypermatrices, because we want to use them for hypergraphs, but it so happens that actually, if you know hypergraphs and you're looking at adjacency data, these actually suggest a specific way of doing algebra on the hypermatrix side. So anyway, this is some summary. I mostly made it so that we could have identified some people that I could contact and we could invite to have some maybe invited lecture or something like that, or however.
Yes.
So James, do you think should I get in touch with some of these people already and see what they say? So you suggest like a invited lecture, or what do you think?
One thing that I'd like to know is how related some of their works are, because if they'll be able to understand what their possible colleagues are doing, then we could meet with several of them. If their works, because if the sparsity imposes somewhat of a communication barrier where someone's working on some particular aspect, someone's working on another particular aspect, then it would be better to meet with them one-on-one. So that's a judgment call. Maybe take a day or so to think about it. If you think that there's an actual good, I don't know what we could call it, like a seminar or a colloquium or something that's themed, where the theme is broad enough that it could readily, incorporate the participation of several of these people, I think it would be nice to, it's like you have kind of a historical thesis. It's like you're all colleagues in one way or another. You've been working on something similar. The question is, will they feel that way? Will that conversation be smooth and collegial? So that's something to think about.
Sure. Okay. So I think it does make sense to have a seminar like meeting with these people. They all work, they have very different backgrounds. Some of them are more physicists, some others are more complexity sciences, some others are more pure math, combinatorics people, but they've all worked on this higher order matrix algebra problem. Like they have all papers on this particular subject, right? So I think it should be fine. So I'll send some emails around, and then I can propose that we could have a meeting and just, because I think that the state of the art of this topic is very vague at the moment. The last paper is from 2021, I think, and I'm not really sure if much is going on. So I think these people would appreciate to have like a get together. And
I'd love to have a, what would you call it, hypermatrix colloquium or something like that.
Something like that.
Yeah. Yes. Good. Well, we've been discussing the possibility of doing something like this. Why not make the first one? Why not make hypermatrices the topic for the first one?
Okay, so now let me join with my Blackboard, and we can use the last 15 minutes or so just illustrating what the theoretical problems are here. Share screen, Blackboard. Taking some time.
Okay.
Yeah. So what is the problem? The problem is that once we, in our conventional setting where we have a binary matrix, which is the adjacency data of some graph, right? We basically have A, I, J, it's the adjacency data of this particular graph, right? Mm-hmm. For IJ being some label, some index labels for the vertices. Now, if you have two such graphs and you want to maybe color them, and you say, you want to color this edge magenta and you want to color this edge blue, then what does it mean to do something like, magenta and then into blue or something, right? Like one into the other, meaning this topology, right? Like one edge after the other. So it turns out, and we discussed this I think last time, it turns out what you should do is precisely take the matrix multiplication of their adjacency matrices, right? We saw this last time. So this is all well and good for one sort of pairwise graphs. Now when you go to higher order hypergraphs, this uniqueness disappears completely. It breaks down into multiplicity, right? It breaks down into this much more sophisticated realm. And so, for example, what happens is that you end up having some hypergraphs that look like this, right? You have some, let's just think of, uniform hyper, three graphs, right? The three uniform ternary hypergraphs. So this thing is now equivalent to something that is adjacency data in three indices, I, J, K, right? And the basic behavior is the same. These are arrays. They can be added. They are vector spaces. They can be additive union kind of operations, all these kind of things. But when you think about the multiplicative structure that is kind of the analog of matrix multiplication here, it's not entirely obvious what you should do here. So the direct analog is that you consider something like, yeah, this edge here and then this edge here, and do something like a binary operation. That's perfectly fine, but in some sense all you're doing is just reproducing this binary matrix multiplication. When you do something a little bit more sophisticated, like for example if you have maybe another edge here that you then color yellow or whatever, right? Then you can start to say, well, when I have these three edges in this particular topology, I'm going to rewrite. This is what we discussed last time. Now, the thing is, eventually you end up with having many index objects that operate with each other in complicated ways. So just to list some examples that we did last time, so you could have this ijp dot b ipk dot c pjk. For example, this is the famous Bhattacharya-Messner, one of the things in the list in the brief history that I had before. We could do the one that kind of resembles like a fish, which is ijp bqr pcqrj, right? So this thing looks kind of like this, where there's three triangles like that. This one looks kind of like a fish, etc. And there are many others. So that's on the operation side. Now, so the problem is spectral theory, right? We never lose sight of what is our objective. Our objective is to go to spectral theory and try to do the eigen problem for this higher order setting. So if we think momentarily what it means to do, what it means to solve the eigen problem in the conventional matrix context, what it really means is that you're basically trying to ask, for which subspaces does your matrix A basically resemble the identity, right? Which is to say, for which subspaces does your A precisely look like something, I don't know, a lambda is the usual, eigenvalue name, right? So for which subspaces does this actually happen, right? So in a way, identity is the key ingredient here, right? Like, I mean, A is the data that we have, and the thing that we are always our measuring rod that we go around throwing is the identity matrix, right? Is this I restricted to a subspace potentially, but doesn't matter, right? And that is the eigenspace when we solve for that. So the problem is, when you go into this higher order context, what the identity is not so immediate, right?
I see.
You don't have an obvious, I mean, there are some obvious choices of identities, but they are no longer unique, right? That's kind of the thing. So there's the obvious thing that everyone is thinking about, which is the Kronecker array, right? You can have the delta ijk, which is always 0 except for when I equals 0 equals k equals 1, right? So this is exactly what you all have in mind. This is like a cube, and it has ones in the principal diagonal of the cube and zeros everywhere else, right? So this is okay. This is an identity. This is in fact what most people agree is the ternary identity, and so this is the identity in general. This is identity hypermatrix or array or whatever. But then you can actually also find things like, okay, give me an identity matrix. So I'm going to call this I, capital I, with indices, I, ijk, is the Kronecker. So it's 0, 1, and so on. But you could also have, for example, let me call it R ijk, and I'm going to define R ijk by saying that this is delta ij. So it's constant in K. It means that if K is your depth, it means that all the cube of values is made of the same matrices, the same slices of matrices, because it's independent of K. And each of the slices is an identity matrix, right? So you have R, G, B, intentional names here, ijk, ijk. And so you basically choose a pair of indices, ik, and here you choose another pair, delta jk, for example. Right? So these are essentially stacks of identity matrices in the 3 possible directions, right?
Yeah.
So these are also identities. And what's very fascinating is that okay, so in the binary world, the matrix multiplication is an internal operation that corresponds to composition of operations. So when you know the spectrum of an operator, and so when you know the spectra of 2 operators and you compose them together, you know the spectra of the composition, right? So composition is a way of somehow factoring the eigenproblem, right? So what's crucial to know is, okay, so the reason why that works is because identity is the compositional identity, right? Identity times a matrix is just the same matrix. So what is very interesting here, well, interesting or complicated, I guess, is that in order to get identity-like behavior, one would like to say, oh yeah, if you just, okay, now I have a ternary operation. I'm taking A, B, C as 3 arguments of some ternary product, right? So you might want to, naively think, all right, so if I have a natural choice of a diagonal matrix that is kind of the Kronecker matrix, the Kronecker identity, you might want to say, so for all A, you just do T of I, A equals to, and then all permutations, right? Like T of I, and T of...
Yes.
T of A,
I.
So, and you want to say this is just A, right? That's kind of the tempting thing to do. One choice, one case. It so happens that for the most natural products, of which probably the most natural one is this one, this does not happen, right? That's not the case, right? So what it does happen is that if you mix T of I and then maybe R and then A, I think I remember this is one of them, then this is A. If you do something like T and I think it's I, A, and B, then that's A. And I think a few others.
Okay. And T of what? G.
Yeah, and I think it's, I don't know.
I, A.
Yeah, A, I, G, or
What
something.
is R and B?
Sorry?
What's R and
G, R, and B.
G, R, and B are these stacks of identities.
What are R and B? Oh, stack. Oh, okay.
Yeah. These are what we call the partial identities or the diagonal identities. Right?
Okay, this
So
Now, G, R, and B, is this like red, green, blue? Or
yeah,
something?
red, green, blue. Yeah, exactly. Red, green, blue.
Okay.
So we call them red, green, blue because when you have ternary operations, it's very useful to have instead of what is the kind of a black, white, inverse, kind of reverse, right? Now you have they are all equally balanced, right? Like so it's this parsimonious notation. But anyway, so this situation makes things much more complicated.
Somewhere.
Say it again, Vukash?
Is there a SU3 group encoded somewhere there?
A what? Sorry.
SU3 group.
SU3.
Yeah.
SU.
Yeah.
Why?
Like.
The color. Quarks are named with colors mostly because of the combinatorics of 3 elements. So it's more like they resemble as, not that this resembles that. So SU3 is nowhere near because there's no complex numbers. There's S3. Everything there's here is S3, right? That's what's here. And S3 is extremely natural to think about in terms of colors, right? Because the cardinality matches of what you want. Because you have this operation of that is saturating, right? You do white, so black is a neutral element. Red, green, blue are elements that combine with each other, but they're neutral with respect to themselves. They're idempotent. And then you have the three mixes, which are, idempotent with themselves, but combine with others. And then you have white, which is this saturating object, right? That is an absorbent object for all the elements in the set. Mm-hmm. So this algebra of colors is the algebra that is kind of lurking behind many of these things. But that algebra is just an algebra that doesn't have a name. I mean, so I'm sure some mathematicians have given some names, but it's just like the algebra of colors. It's not the fact that quarks behave this way is, or there's some kind of connection to quarks. It's deep and understood. Like it's ill understood currently. Like no clear connections. In fact, that's the origin. That's kind of one of the historical origins of ternary algebra in physics, which then turned into these cubic matrices, was precisely because Nambu was thinking in the 70s, maybe we could have a ternary algebra classical algebra whose quantization gives strong force behavior, right? But SU3 was this other candidate theory that Gell-Mann had, and they said, SU3 actually matches much better, and blah, 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 and then the quark model won. So these are kind of competing, analog but competing theories. So it's very hard to see SU3 anywhere near this, because I mean, it's an interesting proposition, but it's a deep question. It's not at all obvious, and if you do complex cubic matrices and try to get SU3 out, it's not obvious at all. People haven't done it. It's not a clear path. But yeah, but it's a very relevant comment, because historically it's in fact how it all happened. Okay, anyway, so and not to get too long-winded with this, because this is a very algebraic thing, but the problem here is then you must choose some operations to have your spectral theory based on, right? Like you can't just say what is the spectrum of a hypergraph, or what is the spectrum of a hypermatrix. You have to say what is the product-specific spectrum at best, right? You have to be product-specific, and the good news, as I said in the beginning, is that these products are actually directly related with adjacency properties of hypergraphs, right? So the reason why I drew these diagrams is because, I was calling back to one of the explanations we had in the past, but the beautiful thing that I think it needs to be exploited, and I think is one of our great assets in this project, at least at this level, is the fact that we can connect the abstract algebra directly to adjacency properties of hypergraphs. And this is something that's not been tried before. So, there is some hints in Edina Gann's literature. In his papers, you can see a hint of this, that he's saying, well, this is kind of the combinatorics of how you associate several vertices and so on. But he's by no means saying, oh, this is the adjacency matrix of a hypergraph and we're doing this operation rewrites. He's not using this formalism at all, right? It's kind of hinted there, and it's implicit in some sense. So what that means that you eventually turn this problem of spectral theory of hypermatrices, you need to filter it through this underlying problem of what motifs are you looking after, right? And so my initial suggestion, especially to get something that everyone can see and we can test things experimentally maybe and so on, is maybe that we should study this guy, because there is literature about it. There is, in some sense, maybe someone disagrees, but in some sense, this formula is kind of the closest analog of matrix multiplication for cubic matrices, right? Because binary matrix multiplication, just for visual aid, I'll write it here, is based on this formula, right? So if you look at it very generally, what you see is some number of elements, some number of matrices being contracted with all of the others, and following some permutation pattern of the indices, right? So it means that the second index is contracted in the first one, and the first index, the second index is contracted in the first one, and the first index is contracted in the second one. So analogously, if I write ABC completely generally, if I want to do as close as possible to that one, I would say, well, I have to contract one index among all three, and each of them has to have a different permutation position, right? So then you will write, in the first one you will write in one position, second one in another position, third in another. So that's exactly this formula, right? So in a way, it is kind of the closest analog of binary matrix multiplication. Of course, there's arbitrary generalizations of arbitrary order of this kind, right? So I would suggest that we study the spectral theory of these things, because that's what people have done in the past in these papers, right? So they have some preliminary results about spectral theory for this particular matrices, and so we can maybe run some experimental kind of tests of whatever spectral measures, complexity measures we expect to get with this particular spectral theory. Because the alternative, by the way, I'm suggesting this because the alternative is to go off and actually develop our own spectral theory for hypermatrices. And I think that's a huge project. Like, I mean, that's probably like, I don't know, years long to even properly scope and everything. So I think at the moment, I'm not saying at some point we won't actually venture into that.
We can, but it's a long-term goal.
Yeah, exactly. So
yes.
At the moment, I think we should focus on what is promising and having some non-conventional, sort of non-pairwise example that is more minimal, that is much more computationally attainable, because the kind of hypergraphs that we can do is much easier. And then we can directly contrast with the literature, and then when we invite them, they will, we will be talking about their stuff in some sense. Yeah. Right.
Good. Well. Okay. Interesting.
So yeah, that's kind of the overview.
My only question is, what do we risk losing? Let's say we do an initial report just based on this particular guy. We don't consider the others.
Yeah.
What do we risk ignoring?
We can always. I would say if we do write something that's public and forward-facing, outwards-facing. Sorry, I would always list the possibilities, because these have been enumerated.
Yeah.
So
sure.
So it's much easier to say, okay, these are the possibilities at this level of depth, and we're going to focus on this one for this and that reason, right?
Yes, we can include that as a caveat, and we can indicate to the reader that we're aware of the other possibilities, that we're picking this one for the purpose of delivering research results in a somewhat timely way, and acknowledging that really the exploration of these other possibilities could very well be its own separate project, which, if we think it's sufficiently important, we might very well do. But the question is, what do we risk in terms of the quality of our research? What do we risk ignoring if we only consider this one somewhat better documented case, and we don't consider the broader spectral theory?
Yeah, we risk the fact that maybe there's actually a good case to be made for considering two instead of one. Because
is there another good candidate that we can consider?
Well, there is this candidate. There are three candidates that to me are the most promising. The three topologies, which are basically the three topologies you can make out of three hyperedges, right? Ternary hyperedges, which is, you have this topology, you have, which we call the cone, because it's like a cone, it is a tetrahedron without a lid, within one of the faces. And then you have what we call the blades, because it looks like the blades of a fan or something. So three triangles that share one of the edges, right?
Yeah. Yes.
And then there's the Treeforce, right? So these three.
Did people actually call it that, or is that a Zelda reference?
So we called it that in the paper, so it has a name already. Right? So these are the three topologies that are natural. Now, these contractions here, the contractions that occur at the meeting points,
yes,
these two are three-way.
Oh, I see.
This one is two-way. So, but even if this last one is two-way, which in some sense you can break it down to multiplying this as usual matrices. By the way, when I say two-way, it really means like matrix multiplication in the usual sense, because you just take the remaining of your hyperedge and it just behaves like a single index, and it is just matrix multiplication. Even if it's two-way, the product will encompass all three triangles at the same time, meaning all three hypermatrices at the same time, right? So it is equally ternary, and it's equally unbiased, it's equally symmetric among all three, right? So to me, these are the three promising characters. If we're going to do experimental work, I would actually probably just go with these three instead of just the one, if we want to really make the case of we are doing more than just spectral theory that is canonically defined because there's only one operation. Because I think that the most promising one, if I were pressed, it will be the first one, and it's the one that is mostly studied already. But the one thing that I see missing in the literature is the fact that there's only one, and so they seem to be replicating this mindset of there is a canonical notion of eigenproblem, there is one single canonical notion of spectrum, and so on. So maybe we have two or three.
But my concern is, you've already warned me that development of a broader spectral theory could be somewhat of a pitfall. That if we presume that it's easily done, we might, to our horror, find that it takes several months to develop.
Yeah. I don't think.
What about these second two? I mean.
Yeah. So I think I was suggesting to have the three instead of the one, or even just the one, as a candidate for experimental results mostly, not so much for the theory development, right?
Okay, that's a good compromise. I like that idea.
Yeah.
And then okay, so we're gonna take the cone case.
Yeah.
That spectral theory is already somewhat developed.
Yes.
And we can even have a nice colloquium to meet with people who have also been involved. We can experimentally consider the blade example and the Zelda example. Sorry, Triforce example. Wait, Carlos, is it just you guys call it Triforce, or do people in general call it Triforce?
I mean, it is coined in our paper, which is, it's already public and people have referenced it. So.
Yes. Okay, but you guys call it, and other people are adapting. That's great.
Yeah.
Experimentally, we can consider the bladed one and the Triforce one. Okay.
Yeah.
This seems well thought through. And when we do our eventual debriefing following this project, let's raise once again the question of the value of developing this spectral theory further. What we would do with it if we were to successfully develop that spectral theory, how it could be applied, whether or not we should make that a subsequent project. That'll be a question to be raised.
Yep.
But for now, I think that this combination of theoretical treatment for the case where the theory is pretty well developed, experimental treatment, this is good. I like this. Good. Do you save these, by the way, Carlos? I hope these don't just get
these are all
erased.
saved. Yeah, these are all saved.
Okay. Good. Yeah, I'd like to refer back to them.
Sure. Yeah, well, that was what I had to say.
Oh, what happened?
My Zoom crashed. So luckily not all my computer crashed, but actually Zoom crashed.
It's not streaming, right?
It is streaming. We are live.
Oh, I see. It's not streaming.
It is streaming. I mean, I had so many windows. Okay, I might actually misclicked and not crash, because it's weird that it just crashed like this. there's this question in chat. So I should.
Are we still live?
Sorry. Yeah. We are live.
Okay.
Only Zoom. I think Zoom crashed locally in some sense, like because I think I have way too many things open.
Well, it was amusing because you were making some concluding remark like, okay, this has been a good stream.
Yeah. I mean, I stopped sharing, and then it either clicked through and then it actually clicked end meeting, or it actually crashed. I don't know, because it just everything collapsed instantaneously. I normally ask you to, you want to end the meeting or something, and it didn't. It just disappeared.
Well, so wait a second. What did the viewers see during that intermission when you weren't even on the Zoom?
They just saw
What did they see?
the notebook in the background.
Well, okay, that's not terrible. Well, thank you, folks, for if you're still here, for tolerating that. Well, overall, this was a quite good meeting. It was a mixed form meeting. We saw some. I mean, what did I like about it? We saw a plan from Carlos. We saw some nice new functionality from Nick, and we got a kind of a mini formal lecture from Carlos. The fact that we did all of that within the span of maybe 75 minutes, maybe not even 75 minutes, maybe something like that.
Yeah. 80 minutes.
Really excellent. Really excellent. These live streams have come a long way since we first began, so that was quite fun. I'm a bit tired today, so I'm stuttering a little bit, but I really like that. We have another meeting scheduled for Thursday. So in the meantime, guys, I'll communicate with you on Discord.
New office.
And yes, we're figuring out this how to kind of simulate the co-working experience, even though we're all virtual, and now we have a better way to communicate with each other. So anyway, I look forward to hearing about developments between now and Thursday, and let's continue this on Thursday. This was a really nice meeting. Thank you guys very much.
Thank you.
See you tomorrow.
Goodbye.
Cheers. Thank you, viewers.
Bye, viewers.
See you all.